Looks like the ZR1 Corvette will debut next spring. Though we did not permit our media friends to drive the car at Riverside, we did give them the lowdown on the LT5, the 32-valve all-aluminum V8 that will power the ZR1. In less than an hour, engineers explained and actually assembled the LT5, all 500-some parts, while the media looked on.
Gentlemen, start your engine.
And that's the LT5 engine. I want to cover a couple of points first, though, before I introduce the engineering crew. And those are the guys that really have given birth to this outstanding powertrain. Okay, as most of you know, the LT5 was designed for the new ZR1 Corvette. But we're not going to have much talking about the ZR1 per se. You'll be able to see a prototype, of course, and you're going to be able to watch it go through its paces on the track. But I can tell you that we are working closely with the PR staff to set up a pretty good event for this fall. That will be a fun event. You'll get a chance to see the entire picture. And then, of course, what we'll want to do is get your driving impressions of the vehicles. We formed some of our own, I might add. So today we're going to focus on the powertrain all by itself. And I know you're going to have a lot of questions on the ZR1, but I'm sure you'll be able to hold those questions still this fall, and we'll handle them at that time. Okay, the business at hand. Ever since that fateful moment 35 years ago when the Chevy Corvette was born, this vehicle has been not only at the leading edge of performance car technology, in many ways we've literally defined that envelope. From the very start, GM was committed to making and keeping Corvette the world's leader in high-performance street machines. And we've maintained that commitment now for almost 4 decades. Birthday party this year, as you know. Of course, in this business, if you're not constantly moving forward, you're certainly likely to fall behind. And in the high-performance area, you can quickly find yourself falling behind at many miles per hour. You saw some of that yesterday, I think. We had no intention of falling behind, of course, on the Corvette. It needs to be out there in front. And the LT5 engine is our latest expression of GM's continuing commitment to high-performance leadership. In setting up the LT5 engine program, we gave ourselves 4 main objectives. First, we wanted to create a car that was second to none in acceleration. We wanted nothing less than the fastest production car in the world. Second, we wanted to achieve that kind of performance without sacrificing drivability, not only at the high end where you would expect it in that kind of a vehicle, but at the low end also. We wanted a street vehicle that had a kind of a tiger and pussycat kind of a personality. And we knew that that was going to be no mean feat. Third, and this was really an ambitious objective, we wanted to package all this leading performance and drivability into an engine that could still deliver great fuel economy. Now, we didn't want a gas guzzler, not only because GM is absolutely committed to making fuel-efficient cars, but because we wanted to do nothing to jeopardize the tremendous high level of satisfaction that Corvette has established with its customers in terms of fuel economy. And last but not least, we set the task that would fit between the rails of the engine compartment in the existing Corvette. We wanted a brand new engine, but we didn't want one that would require an entirely new vehicle. Now, we knew back in April of 1985, when we began looking at the LT5, that each and every one of these objectives was going to be a pretty tough bogey to meet. So when you take all of those 4 together, we really knew we had a task on our hands. You see, like everybody else, we understood that the 2 of our objectives, the acceleration and fuel economy, are typically mutually exclusive. You can't get one and then the other. Now, I want to highlight the graph here because what it says here is that as you move towards faster and faster acceleration, your fuel economy goes down. That's what I would call a trend line here, and you've got to walk up and down that trend line. You can trade one for the other. The only way to improve is to push that trend line outward, and the only way you can do that is with technology. When we talk about pushing the envelope, that's in essence where we wanted to go. So that's what we set about with the engine, is to get that trend line up and to the right. So it's only by technological breakthroughs could we redefine the economy acceleration equation. And we had to do that in order to accomplish all of those goals that we laid out. And we've been able to achieve that, and that's why we're excited about the LT5, because it really does represent some pretty impressive advances, not only in high-performance engine design, but also in the manufacturing and production technology as well. Now, in order to bring you some of those details, it's my great pleasure to introduce to you Roy Midgley. Now, Roy is the chief engineer of our passenger car V8 engine group, been a Chevy guy for a long time. And what he and his crew are going to do, they're going to literally take you on a tour of the new LT5 engine while you watch one of them being assembled right here on stage. So, Roy, give us the tour.
Thanks very much, Fred. This is going to be a lot of fun today. This is really an engineering show. You're going to be looking at over 500 different parts. We're going to be putting them all together to create an engine right in front of you here. When we're all finished here, the one that's put together is going to be supplemented by one backstage that is all in its pieces, and you can look and ask questions about every one of those over 500 pieces. There's also going to be 4 of us talking. There's 2 of us from Chevrolet, and then there's 2 other fellows, one from Lotus and the other from Mercury Marine, and they're our partners in this whole entire thing. I want you to meet first, though, a couple of guys here are going to be the assemblers for today. This is Ron Oshinsky. Chris, we got to get going on this engine, so start your engine. How'd it go, Rick? What Fred talked about was the objectives of the program. What I'm going to start with here are the major design goals that were needed in order to achieve those objectives. Obviously, when you're looking for performance and fuel economy, you've got to talk about power, you've got to talk about torque. We went to the computer and we found that we needed about 50% increase in power, we needed around 30% increase in torque, which brought it to around that 370, 390 foot-pound and horsepower for the engine. If you're going to do that on a 5.7-liter engine, and you're going to do it naturally aspirated, it obviously has to be a dual overhead cam engine, and that's what this is. We still needed to achieve what is the federally set 22.5 mile per gallon guzzler requirement on fuel economy, and we needed to be able to get the combustion efficiency not just at the high speed but at the low end as well. Now, I might comment here as we go along that as this engine is being assembled, you can watch the engine, but what we're going to talk about is the component assembly in a lot of detail. So if you're trying to follow what we're doing here in the script, or an outline of the script at least, what you're really going to have to do is up here watch the screen. So continuing on with the rest of the requirements on goals, street drivability is obviously a given. We had to be as good as the current Corvette, and probably even better. So there's new features in ignition and fuel control and throttle control. Packaging, I think, is probably the biggest accomplishment on this job, taking the new technology, putting it into a package that met 3 major criteria. First, it had to fit into the existing Corvette. We could not redo the frame, we could not redo the car. We had no change in the hood surface, and it had to be assembled on the same production assembly line as the current base engine. The appearance of the engine obviously had to be a world-class appearance. In the competition we're facing these days, the engine has to look like it is a performing vehicle. So it had to be compact, neat-looking, and have excellent appearance. These days there's 2 other givens. One of them is the mandated requirements of both federal and state emission requirements. That includes the tailpipe emissions, the exhaust emissions, as well as the noise pass-by laws that are in about 8 of our states, primarily California with the more stringent requirement. Reliability is one of those things that within General Motors and the Chevrolet, there is just no compromise these days. That's just the price of entry, and you have to do it on performance as well as base engines. What you see sitting there right now is the engine block. Obviously, it's the major structural component in the engine, so it's a key item. It's an all-aluminum construction. It's an open deck, has individual freestanding aluminum bores, and it's about 90 pounds less than the current production iron block engine. Some of you will be happy to know that this engine has the same traditional 440-inch bore centers that we've had since 1955. And the deck height on the engine from centerline to crank is the same as the small block has always been. But it's about an inch shorter in the rear because we got rid of the distributor and the drive that went down to the what was the single camshaft. The displacement, as I mentioned before, is 5.7 liters, the current production and base engine displacement, but it's achieved with about a 1/4 inch longer stroke, 93 millimeters to the people from the continent. And it's a 99 millimeter bore, which is about 1 millimeter smaller than the current 4-inch bore. So that ends up with a 107 bore-stroke ratio, and I got to tell you that's a coincidence, but it's the same bore-stroke ratio as we have on the 5-liter that's used in some of our other cars, including the Camaro. Now that I've talked about the block, I'm going to go on to what I would classify as the backbone of the engine, and obviously that's the crankshaft. The crankshaft needed to be significantly stronger than the nodular iron crank that we use on today's engine. Longer stroke required that. It is a nitrided forged steel crankshaft. It has a very unique feature. I think it may be unique in the world, and that is that it has end-to-end oiling so that the oil is centrifuged from the center line of crankshaft to the outside. So the oil enters at the front where the oil pump is, goes through each successive main bearing, up through the pin, down to the next main bearing, and so on through the entire length of the crankshaft. In the center of the engine is the ignition timing disc, which is integral with the shaft. That disc has on it 9 marks, 8 of which are the location of each of the individual cylinders. 2 of them are at one location, and that's obviously top dead center for cylinder number 1. Although the pins on the crank are the same diameter, and therefore the small end of the rod is the same diameter as the current production engine, the main bearings are 0.31 inch larger in diameter. So they're 70 millimeters. That allows for the 7,000 RPM operation that we expect from the engine because it provides there the torsional and the bending stiffness that's required and the extreme increase in performance. While we're talking about the crankshaft lubrication, let's go on to the rest of the lubrication system. What you see here is the oil pump. It's crankshaft driven, and it's a gerotor type oil pump. It delivers about 9 gallons a minute at 7,000 RPM. And a unique feature of that is that it's thermostatically controlled lubrication. And that is that the oil is cooled through a cooler that goes through this housing. What happens is that the oil runs through the cooler beginning after the oil temperature has reached about 190 degrees Fahrenheit. So we control the viscosity of the oil by controlling the temperature to essentially, after warm-up, to within 180 degrees to 265 maximum degrees Fahrenheit, which we would expect to see even under the maximum we'd expect to see even under the most severe driving conditions out at desert proving grounds, 100 degree or more ambient. The oil feed is a parallel oil feed to the cams and to the crankshaft. In other words, it goes from the pump through that housing, then straight up the front of the case, up to the cylinder heads, and then goes down each cylinder head and delivers oil to the camshafts and the journals. There are cast-in oil drain holes in the cylinder head and in the case and in the pan and in the lower crankcase. There's altogether 4 on a side or 8 altogether, and that supplements the oil and the blow-by that comes up through the chain cover in the front of the engine. I just mentioned the lower crankcase assembly, and that's unique for Chevrolet engine also. Actually, the lower crankshaft or crankcase starts at the split line, the center line of crank. It's really, therefore, part of a two-piece crankcase assembly. The lower crankcase is made out of a nodular iron main, made out of aluminum, and then it has cast-in-place nodular iron caps. So what it really amounts to is the lower case is a saddle of sorts, which ties together the crankcase bulkheads and the rails with 28 different attachments, giving the maximum stiffness, and we feel that's essential not only for the structural durability, but to the noise suppression for both pleasability and pass-by. The crankshaft timing sensor is mounted in the right-hand side of the lower crankcase, as you see in the picture. And it's electromagnetic pickup, and it plus one at the camshaft is what assists in the ignition system. There is a cast-in oil pickup in the lower crankcase. That pickup then indexes with the cast oil pan by an O-ring seal and then down into the screen and pickup cast aluminum assembly that is mounted to the bottom of the oil pan. I think at about this point, we've got the engine at the spot where we can talk about some of the components. So instead of proceeding before with the rest of the engine, because the story continues to get more complicated, maybe what we should do here is I'll stop for a moment and see if there are any questions about the portion that I've discussed so far.
I see hands rising all over the place.
Okay, Ralph?
We just had a potty break. No.
What percentage of inputs on the design of this engine came from Lotus in England, and what percentage from Mercury?
Could I ask you the repeat on that, Ralph?
Repeat the question.
What percentage of inputs on the design of the engine came from Lotus and from Mercury?
Okay. Lotus and CPC, from the beginning, were integrated into the design. The criteria for what we needed to achieve was a totally Chevrolet requirement. The engineering detail obviously piggybacks on both the experience of Lotus, which is substantial as you can imagine, as well as our own within the V8 group and the entire CPC engine groups, as well as some of our staff and the research departments. So if you I'm going to say that from an engineering standpoint, we're talking about a 50-50 deal here. And the synergism when you do that is absolutely amazing.
What process do you use for holding the iron main caps into the aluminum girdle?
The iron caps are actually cast in place. It's a permanent mold system. It is locked in place in the casting, so it has a physical lock. But more importantly, those caps actually tie to the bulkheads at the side. So the iron goes in the aluminum, but also goes entirely across the width of the case and screws into the rails on the side as well.
The question was,
Not the L-fin process or something
no,
similar?
you mean like on cylinder bores?
Right.
No, sir, it is not. It's a larger physical interference than that would be.
Earlier this morning it was mentioned that there were some general concepts that are in common between the Ilmor Chevrolet and that engine. Could you tell me at what time in the development and to what extent there was an exchange of general information between the Indy program and this?
Well, I got to tell you that Ilmor's right down the street from Lotus, but the communication on the commonality between those engines occurred at Chevrolet. And the extent of that is, I would say, the synergism, again, that you heard Fred talking about. What you learn about what it takes to make an engine run at extremely high speed is something that I'm going to say from an engineer's standpoint, we all learn from errors. And so the problems that occurred on the Ilmor during development, associated with oiling, any durability problem we picked up on. There was no direct involvement where we transferred engineers from there to work on this engine or vice versa. Hey, Ralph, there's several over here.
Since you're clearly not sharing many, if any, components with the current 5.7-liter engine, why did you stay with that displacement? Why were you concerned with the bore spacing? For that matter, why did you stay with an 8-cylinder design?
Well, the 8-cylinder design was one of the big things. I think the 8-cylinder design probably is one of the most efficient packages that has ever been devised for an engine. Now, there's going to be people who make others who debate that, but that's still my feeling. The decisions on retaining the bore centers are fairly obvious. If in fact you are going to get any commonality between one engine and another, you better be able to have the bores line up with each other. So if we're ever going to use interchangeable parts between a dual overhead cam and a current iron case, then you need to have bore centers. That is absolutely fundamental to manufacturing and the design of an engine. So it starts right there. In addition to that, there's, for instance, for about every 40 thousandths of an inch increase in bore centers, for example, there would be around a 21-pound increase in the engine. So you just do not arbitrarily increase the size of an engine unless you absolutely must do that.
Keep on moving here so we can get on with the rest of this program. What you're going to have is a whole lot more, grist for the mill here in a minute as we unveil this thing.
Okay, I will continue then with what I've dubbed the heart of the LT5 engine. Obviously, the combination of the liners, the piston, and the combustion chamber are what comprise the combustion area of the engine. So what we're looking for is the combustion efficiency to achieve both the power and the fuel economy and to retain the hydrocarbons and keep the emissions under control in the combustion chamber. What we're going to do now is bring into the picture some of that flavor that we were talking about, which is the international flavor of the engine. And the best guy to do that, and the fellow in the group here that I've been told uses the King's English, which he interprets as the correct English, is Mr. Ian Doble. Ian is the general project manager at Lotus, my counterpart over there. He's been an engine expert for almost all of his life. He's been in the auto industry 17 years, 13 of those have been on engines, and he's obviously had some good teachers working with both Colin Chapman and Tony Rudd, who is here today, by the way. So again, not to overuse the word, but the synergism that Lotus and Ian brought to this program, and the racing excitement and tradition, as well as the innovation, make him an expert and needed member of the team. So, Ian.
Good morning, ladies and gentlemen. Thank you very much, Roy, for a very glowing introduction. And yes, it's been a very exciting 3 years here, working on the LT5 engine. And Roy makes a big deal about synergism, and it's the synergism that's made it all happen in the 3 years. Talking about the heart of the engine and the combustion chamber, it's made up of 3 components, really: the liner, the piston, and the combustion chamber in the cylinder head. And to start with, I'd like to just start with the liner and work my way through the 3 components. It's a freestanding forged aluminium liner. It's coated with a nickel silicon hard-wearing resistance, 4th thou thick. It has an integral flame ring on the top of the liner to give protection to the head gasket and also to eliminate any spots for hydrocarbons to linger. Being forged, being freestanding, it's of uniform thickness, and that makes sure that we get excellent heat transfer around the whole of the liner, so there aren't any hot spots or any areas which may promote detonation of the end gas. The other part of the system, of course, is the piston. And in this engine, it's a die cast or permanent mold casting with metal inserts in the skirt to control the expansion rate so that we don't get excessive piston noise, either cold or warm. And it has a machined combustion bowl in the crown. It's machined so again that we can maintain the combustion chamber volume accurately for the high compression ratios that we're working at. It has a conventional ring pack, even working against a hard Nickel coating. It has 3 cast iron rings, the top one being barrel faced, the second one being taper faced, and the third one is a normal oil control ring with a spring backing. The whole assembly is connected to the forged steel connecting rod via a free-floating pin. We call it a gudgeon pin in England. This is necessary because of the high piston speeds, and we're working with a 7,000 RPM engine with a 3.66 or 93 millimeter stroke. As you can imagine, we need to have a very fast burn rate to achieve high piston speeds, and we need a good gudgeon pin and conrod to hold that together. We've gone away from Chevy tradition somewhat with the connecting rod bolt, and we just have a bolt that's threaded into the conrod itself rather than the nut and bolt that the Chevy normally traditionally use. Let's say, fast piston speeds and high engine speeds need a fast burn chamber, and that takes me to the heart of the combustion chamber itself, which is the cylinder head volume. We've got 11.25 to 1 compression ratio, again for our fast burn. And again, to maintain the volume down, we have a tight inlet and exhaust valve angle. The included angle is 22 degrees, 10 degrees on the inlet valve, and 12 degrees on the exhaust valve. And the valves themselves are very large in comparison. We've got 39 millimeter inlets and 35.2 millimeter exhausts, all in a 99 millimeter bore. And all this goes to help us get some 40 pounds a minute of air through the engine at maximum power. The exhaust valves themselves are stellite faced on the seat. The spark plug is centrally mounted, as one would expect in a pent roof chamber of this sort, to ensure that we get minimum flame travel at maximum flame speed, and there are no end areas which will promote detonation. We have a cloverleaf squish area which is unique to this combustion chamber, again to ensure that all the gases go to the central spark plug and get for good fast initiation of burn. All this technology goes to give us a high performance, high efficiency combustion chamber that allows us to achieve the fuel economy that we needed to make sure that we got the gas guzzler even with a 370 or 390 horsepower engine. The basic calibration is done on the premium fuel, but because we have such a high thermally efficient combustion chamber, we can actually run on regular unleaded fuel without making any loss in performance or degradation to the engine at all. I appreciate a very fast rundown of the combustion chamber, which is the heart of our engine, and as it is a complex subject, we take another question and answer session very briefly before I hand you back to Roy.
We'll take a couple of questions for Ian, and then we'll move right on here.
Okay, pistons. Why cast rather than forged?
Primarily cost and also weight. You can get more weight out of the piston because you can allow it to go re-entrant within the die, which you can't do with the forging.
Here's one.
I've heard a couple of different horsepower ratings quoted. What actually is it officially?
Officially, we're somewhere between 390 and 370 horsepower.
Officially.
With respect to the fast burn characteristics of the combustion chamber and the speed of flame travel, can you tell me how or what considerations went into the actual design of the combustion chamber and the degree of bushiness of the flame front?
Very difficult to explain that in a few words up here, but the technology and the design of it is such, I think, as you can see from the cloverleaf, to make sure that we get minimum flame travel and a uniform flame distance so that we don't have any trapped areas of end gas which could cause detonation.
One more?
Yeah, is there a failure mode? What happens when the owner blows the radiator hose and the engine heats up? Does the engine protect itself, or does it drive itself to destruction?
it'll drive itself to destruction at 170 miles an hour, I expect.
Well,
It is, to be serious, I'm sorry, there is some obvious protection within the system with temperature sensors connected to the ECM that will also shut down the fueling so that we go on to our normal mode of operation. And there are warning lights for check engine lights so that the driver will be notified if it did lose water.
well,
So yes, there are some backup systems.
let me supplement that. Now you're getting into this fall's presentation, but there is a coolant level sensor in the Corvette system. In other words, when the coolant comes out of the radiator, you get an early warning there. So as the coolant drains, you get the first signal. If you persist in spite of that signal, the second thing would be the cylinder head temperature, and I suspect you get a little bit of detonation after a while, too.
Okay, go ahead.
Okay. Okay, thank you.
Thanks, Ian.
Thank you.
Ian talked about the heart of the engine. I'm going to finish up because the heart of the engine obviously is in the cylinder head. The cylinder head is an all-aluminum permanent mold cast head with sintered iron valve seat inserts as well as iron valve seat guides, dry guides for the valves. It has a 4-bolt head pattern, different than the current engine which has 5, which allows for the very efficient dual inlet ports and dual exhaust ports, as well as providing a better cooling path for the 95-gallon-a-minute water pump we've got on this engine, which is key in the power development as well. Back to the packaging accomplishments, though, there are several things on the cylinder head that provide for that in this engine. First, it has a very compact valve gear, and that valve gear, by the way, still left room for a hydraulic direct-acting valve lash adjuster. The camshaft bearings are integral in the head and in the cam covers. So that is line bored through there, and we're going to talk about that in a few seconds. The overall width of the engine then is at the point there at the cylinder head, the corner of the cylinder head at the rocker covers, is 675 millimeters, and that was absolutely mandatory in order to fit between the rails of the Corvette, and as an outstanding achievement in packaging, we think. I've covered several of the major castings already, and you're looking at several of them. We have not touched on the other most important end of this business, and that's how you get it manufactured, and that's the simultaneous engineering part of any program. I want to introduce now Mr. Bud Agner, who's plant manager at Mercury Marine. He's Mercury Marine plant manager in Stillwater, Oklahoma, and that's pretty all-American engine, by the way, guys. The manufacturing engineer in the automotive industry, and now he's been in the marine industry for the last 10 years. What Bud and Mercury Marine bring to the equation on building and manufacturing and designing this engine is an outstanding aluminum casting expertise. Flexible machining center equipment in the hundreds in the plant. And then the exceptional quality that flexible machining equipment brings to you at a moderate volume, which is a major achievement. You can do it on high volume equipment. The flexible machining centers are critical to doing it on a moderate volume. And then obviously the Mercury Marine experience and a tradition of very high performance engine building. So Mr. Bud Agner.
Thank you, Roy. Ladies and gentlemen, let's hold the thought of simultaneous engineering as one of engineering and manufacturing working together from the onset to develop product and process to assure consistent quality. Process reliability has been designed into the manufacturing process utilizing the simultaneous technique between Chevrolet, Lotus, and Mercury. It has been my great pleasure on this program to work with not one, but 2 fine engineering organizations in Chevrolet and Lotus. One of the major challenges for manufacturing on this engine is the line boring of the camshaft bearings. In order to get the 22-degree included angle and the compact valve train, the upper camshaft bearings had to be incorporated into the valve cover. This means 6 bearings, 26 millimeters in diameter, have to be bored with a 1-inch boring bar unsupported for 27 inches. In order to do this, a precision boring machine was designed to hold the boring bars in tension while boring. Heavy metal boring bars were designed with diamond tooling to allow us to maintain the tolerances and finishes required for this engine. A more traditional approach is used in line boring the main bearings of dissimilar metals. The crankshaft crankcase being aluminum and the lower case having nodular iron inserts. Our experience in this area with our tooling made it possible to hold the tolerance on all 5 main bearings within 5/10 for size and roundness. Mercury has extensive experience in metal-to-metal joints, anaerobically sealed. The LT5 engine requires metal-to-metal joints between the upper case and the lower, and the cam cover and the cylinder head. The anaerobic seal is applied utilizing a silkscreen process for uniformity and a leak-free joint. The flatness required for these finishes mean we surface mill with cutters using diamond inserts at extremely high speed, up to 6,000 surface feet per minute. Mercury has considerable experience in casting and machining aluminum parts, as Roy mentioned. Our processes have been developed for maximum flexibility at intermediate volumes. We utilize computer numerical controlled machining centers wherever possible. This type of equipment fits intermediate volume needs, but also produces parts with extreme accuracy. A typical high volume cylinder head transfer machine would probably refixture a cylinder head during the machining operation 30 to 40 times. Our setup on flexible CNC working machining centers, we only refixture the cylinder head 4 times, thus minimizing the stack-up of tolerances and providing for better relationships, being critical to the features of the engine, such as valve seats to valve guides to cam bore, crankshaft bore to cylinder bore sleeve, and liner seat to combustion face. As mentioned earlier, process reliability has been designed into the manufacturing process utilizing simultaneous engineering. Statistical process control is used throughout the manufacturing process to check the quality of the LT5 engine. A direct computer-controlled coordinate measuring machine with SPC software is dedicated to the layout inspection of the major components of this engine. Mercury has extensive experience with this state-of-the-art system, which assures reliability of our manufacturing process. All engines will be fully dressed, hot tested on a dynamometer test stand. The LT5 engine is dynamically balanced on the test stand while running under its own power. We've been able, as shown here on the video, to stand a nickel on top of the plenum on this engine while it's running at idle at approximately 650 to 700 RPM and run it up into the range of about 1,500, and it sits there just as you see it there today. That's a smooth running engine. Provisions have been made to check the wiring and electronics as well. All these things are being done to assure maximum customer satisfaction. And at this time, I'll try and answer a few questions as well.
Questions for Mr. Agner?
I was curious as I was watching that valve cover sealing process, what about the guy at the Chevrolet dealer that's got to, for some reason, pull the covers on this motor? How does he go about resealing it properly?
The point on that, to reseal an engine in a repair mode, use the same type of anaerobic sealer, and it can be spread out and trained. And in our marine business, we have found out that the dealer organization, if trained, can do an excellent job of maintaining the original integrity with the anaerobic sealers.
We used, is this still on?
Yeah.
We used anaerobic seal on as far back as the Corvair on the split halves of the case on that, and the dealers had no difficulty with that. I'd hope the covers never come off this one any more often than this case was split on that job.
The word moderate volume keeps coming up. Exactly what sort of volume are you looking at when this thing's up and running?
Well, maybe I can comment on that. 1,600 a day is what is an economic increment on a high volume application. Mercury, I think, Bud has told me, runs around between 10 and 50 a day, and that's what I would classify as a moderate volume, and where their expertise is in the marine industry.
That's correct, right. That would be in the area there of the 10 to 50 units on a daily basis.
Over here, take about one more question.
Pardon me? We could build engines within that. How many? That answer was too broad. How many do we plan to build is the answer, and the answer is that we can build within that range according to demand. That's 4,000. That's 4,000 to around
8,500.
Yeah. Okay.
Yeah, are the castings for this engine produced in this country?
Pardon?
Are the castings produced in this country?
Some of the castings are produced in this country and some of them are abroad. If you'd like a detailed list, we could probably discuss it later, but the cylinder heads, for example, are in England. The piston liner assemblies come from Germany. The block and lower case is done down in Texas, just to name a few. We also are casting 5 major castings in our own shop in Stillwater, Oklahoma.
Dave McClellan, how many a day? Does that?
18 a day is our planned starting volume.
Okay.
Yes, I have one more question. Can you shout it out over there?
Could you explain that? And supposing you have a motor that needs a little bit of work to bring it into balance, where do you go from there?
Okay, we have balance equipment that is hooked up to our dynamometer test stand, and it's a very elaborate test stand with full computer controls. And when we find out where the unbalance is, we stop the engine and we insert heavy metal carbide pins in both the flywheel or the TV damper in the front to achieve that balance. We balance the engine total in mass balance to less than 1/2 inch ounce. Thank you, Roy.
Thank you, Bud.
Thank you, Bud.
Now on to the induction system requirements. In order to achieve both the power and the torque that this engine is expected to put out, obviously what we're talking is volumetric efficiency. But in addition to that, that's airflow. The other part of it is how do you control that airflow and the fuel metering to achieve the very precise drivability and emission control requirements of the engine. So that what you really end up with is an induction system requirement that provides both the tiger as well as this kitten personality that Fred alluded to before. The best guy I can think of on the team to explain that is Larry Banning. I've worked with Larry for a lot of years. He started off at the Flint V8 engine plant, resident up there, and then came down to engineering and has worked in both the base engine design and the induction and fuel control systems designed for his career. He's a real asset to the program. So Larry, I'd like you to come up and go through the induction system with us.
Well, thank you, Roy. Good morning. You've heard a great deal about the type and functionality of this.
You
You've heard a great deal about the tiger and pussycat personality about this engine, but there's an intermediate stage that makes this engine even have a more lovable personality. That's accomplished through our throttle control system. And on that throttle control system, we have a total of 11 throttle valves. 3 of those throttle valves are located in the throttle body, and the other 8 throttle valves are located in the cylinder head and the secondary runners, controlling air to the secondary inlet valves. It's really a 3-stage type throttle valve system, and I'd like to talk to you beginning with the first stage. The first stage is controlled by the small 22 millimeter diameter throttle bore, and it delivers up to 30 horsepower from the engine. During that first stage, with the small primary throttle valve in operation, of course, the 8 inlet valves are also there. In the second stage, that's what we refer to as the intermediate stage, the engine will deliver up to 200 horsepower. And during that second stage, all 3 throttle valves of the throttle body are operational. Also, the same 8 inlet valves that were operational in stage number 1. The third stage is the full power stage. During the full power stage, the 8 secondary port throttle valves join those 3 that were already there, making all 11 throttle valves operational, providing full power. And of course, at that time, all 16 inlet valves are operational too. For you to be able to enjoy the full power in the third stage, there is a total of 4 different requirements that must be complied with from the ECM viewpoint. First of all, there's a separate key, and the key is installed in the console, and it has 2 modes. One is normal power, which provides stages 1 and 2, and then there's a full power choice that you can make with a key. During the full power choice, of course, you have this third stage operation and also stages 1 and 2 as you choose. The second requirement to enjoy the full power stage is the coolant. If you start the car up in frigid weather, it takes a while for the coolant temperature to come up to speed, and we make sure you don't get full power operation until the oil viscosity is acceptable for the lubrication system to provide what we want there. The third one is something which you all enjoy. It's driver dependent, it's pedal to the metal, related to throttle position sensor. The fourth one is something we hope customers never experience, but there cannot be an engine check light on or a diagnostic code that is permanently set to be able to get in the full power mode. Now, we've talked about the throttle air control system, and we need to spend a little bit of time moving into the speed density system as well as the fuel system. This engine is speed density as opposed to the current base Corvette L98 engine, which is mass airflow. The ECM uses a manifold absolute pressure sensor that's located at the rear of the manifold plenum. It uses a manifold air temperature sensor that's just in front of the throttle body. And of course, it uses the engine speed coming from the ignition system crank sensor. We already know what the volumetric efficiency is of the engine. That's in a table in the ECM. Through those 4 ingredients, the ECM is able to calculate what the airflow would be for this engine. To go with the airflow, of course, we have to have the proper fuel. And I'd like for us to just spend a little bit of time trying to chase the fuel route path on this fuel rail. The fuel actually comes in at the right rear corner of the engine. It comes in, and it is split into 2 paths, and it goes down an inner tube on each side of the rail, going all the way to the forward part of the rail, the front part of the engine. And then it returns, being consumed by the injectors. Whatever fuel is left over comes back to the rear and comes back out through the pressure regulator and returns through the fuel return line back to the fuel tank. You'll notice that there's a total of 16 injectors. 8 injectors are for the primary system, and the other 8 injectors are secondary for the secondary side of the system. With this particular routing and fueling and so forth, it is not possible to end up with any stale fuel in a system at all. And of course, we're able to purge vapors out that might occur during hot soak very, very quickly, and so we'll have the kind of startup and drivability that we all desire. To go along with the fuel system that we have here, the 16 injectors, the Multec, made by Rochester Products, we get into the area of the oxygen sensors. We have a dual oxygen sensor system. They're actually heated oxygen sensors to help us with the emission control side of the business. The oxygen sensors are located on each side of the engine, right from where the exhaust manifold outlet is, just before where the catalytic converter begins. You notice that the catalytic converter is very close to the engine, closely coupled. That provides early converter light off for emission control. You'll notice also it's large in size, and so we're able to have the low restriction on the exhaust system side for the kind of performance we seek from this engine. I think next we can go ahead and move on to the ignition control system. The ignition control system has a number of components in it, but some of the major ones are tied into the crank sensor, the ignition module, the 4 coils, and also an ESC sensor. This is really a direct fire type of ignition system. Our current Corvette engine has a high energy ignition distributor, but with the LT5 we've eliminated all moving components. So there will not be any change with time due to wear and that type of thing. The direct ignition system is a preset system so that when the engine is assembled, the spark is preset and it's fixed. It is not adjustable. You can see here on the engine, those of you on this side, on the left-hand side of the engine, the ESC sensor. As has been mentioned to you before, this engine has outstanding spark characteristics, so very seldom do we really have to use that ESC sensor to take care of detonation. But in the few occasions when we do experience it, at very low RPM, wide open throttle type thing, low octane fuel, hot weather, it is there to provide the kind of detonation protection that will not be noticeable to the driver at all. Well, we very quickly covered 3 important control systems of this engine: the throttle for air, the fuel, and the ignition system. If you have some questions, we can take a little bit of time to talk about those.
You mentioned the VE. What is the volumetric efficiency of this engine at peak torque?
Volumetric efficiency of this engine at peak torque. I can't give you a specific answer on that, but
I think we'll have to that one at the SAE convention.
We can tell you it is very good. The whole induction system and the exhaust system were both designed with certain targets in mind in terms of the amount of depression in the intake system as well as the amount of back pressure in the exhaust system. There are some modifications being made as we go through development and so forth, but they are very good. They're highly outstanding.
Well, the high 90s, if we want to.
How is vehicle
We'd
speed?
have to get into the specific detail of that.
How is vehicle speed limited, and what is that limit, please?
That's really going to be a vehicle consideration, and it's quite simple for us to be able to control vehicle speed as we choose to as we go further down the road. It will end up being controlled by fuel type of shutoff. Of course, since we have the 3-stage system that I told you about, we're able to go ahead and shut the secondary port throttle valves when the time is appropriate also.
Hello?
Hi.
Okay, you mentioned that there's a volumetric efficiency map in the ECM, and in addition to some other spark maps and whatnot. Is there any adaptive or learning function in any of those, or are those set at the factory? In other words, as the engine breaks in and eventually wears, will the engine adjust those maps accordingly?
Yes, there is a very tight control on that. we have what you probably refer to as keep alive memory. And as the system learns what the volumetric efficiencies should be, perhaps, as time changes, as corrections have to be made for temperature changes and fuel changes and that type of thing, all of that is in there for the keep alive portion. And with the oxygen sensors that we have, we maintain very close tolerances, tight around that stoichiometric window, so that we have excellent converter efficiency for emissions. And to do that alone, we have to have keep alive memory. We have to be able to learn what that is, and probably the biggest single variable of all is the fuel that comes from the canister, the charcoal canister, while we're purging the fuel out of there, and depending upon the loading, how much fuel is in there and how much we're purging from there, and that's an area that's difficult to figure out. Is your canister completely empty of fuel, or is it just getting filled with fuel, that type of thing? So keep alive memory, learning as we go along, is a key part of this whole program, and that memory is kept there after the engine is shut down for the next application.
Len?
Two questions. One, would you repeat the steps 3 and 4 that are necessary for the engine to operate at full throttle, full horsepower?
Okay. Steps 3 and 4, I think the order I gave you, better look back at my notes. Step number 3 I told you was TPS, didn't I? Throttle position sensor. You have to be into the accelerator pedal a certain amount before you can get into stage 3. Anytime you go to wide open throttle, you'll be at stage 3, providing the other 3 steps are complied with from the ECM viewpoint. It varies with operational mode. So you don't have to be wide open throttle on the accelerator pedal to be able to get into stage 3.
And stage 4 is?
Stage 4? Oh, I'm sorry. You're talking about the 4th requirement?
That's correct.
Okay, I'm sorry. The 4th requirement that we have to comply with is to make sure there is not any engine check light or diagnostic code that has been set in the ECM. If there is a diagnostic code or an engine check light operating, you cannot get into stage 3.
The other question is, what happens with alcohol-laden fuels? What effects do they have on the operation of the engine? Either methanol or ethanol.
Of course, we get into that area and we start thinking about spark sensitivity. We haven't talked with you much about that, but this engine, even though it's 11.25 to 1 compression ratio, it's calibrated to be able to run with 91 octane fuel. When you get to 2,000 RPM or higher, that is where a crossover curve and a spark characteristic takes place. That's very desirable, extremely desirable. And at that point, your minimum spark for best torque is less than what your borderline detonation spark would be. We do not anticipate any difficulty using the special alcohol fuels. This package, we believe, will run with any fuel that's available to the public as long as it is regular unleaded fuel.
One more over here.
You stated that the timing was fixed. In fact, isn't the timing done in the ECM and all you're using the engine mechanicals for as a reference point?
Well, the timing becomes a very complex issue. When I mentioned that it was fixed, what I mean is that it all goes together and is locked up, and you end up with 6 degrees before top dead center on your timing. And during the crank mode, you will have 6 degrees before top dead center timing. And as your engine starts up, then your 6 degrees changes and comes up to where the engine wants to be. You cross over the 400 RPM threshold point, and then you move from the backup mode into the normal operational mode. So the timing is highly flexible once you get into the run mode that's 400 RPM or higher, and it is calibrated to give you whatever the engine will best perform with. It is not at all like the distributor, centrifugal curve, vacuum curve combination. It is able, the ECM is able to go ahead and calculate what the proper spark advance should be based upon the operating modes of the engine, and the engine ECM sends that information to the module of the ignition system, and the ignition system actually releases it at the proper firing time then.
Okay, one more.
Okay, quick one. Now that they've got this nicely screwed together, Are they going to do the Clara Johnson test? Secondly, why, if one of the design objectives was to build the fastest production car in the world, is there any consideration being given to artificially limit top speed on the car?
Well, number one, when I see that Clara Johnson test, I have some different feelings. I wonder about the confidence level. I sometimes say to myself, why do they have to start it? They should know it should run. So I hope that from our viewpoint and with the confidence we have in the design and Mercury Marine's ability to produce an engine like this, we know it's going to run and it's going to be an engine that's really going to be outstanding in that respect. In regards to why do we have to have a top speed and so forth, there are many...
I think the answer to that was the one we just heard from McClellan here from the audience, which is we didn't say yet that we will. But there are things like tires and other vehicle considerations with the engine that must be sorted out. We have to know that the entire vehicle is compatible with that speed. I think that's the answer at this point.
As from the engine viewpoint, Roy, we'd probably say it's a Tiger, rearing to go, and it doesn't care how fast.
Absolutely. Absolutely.
Okay. Very good.
Okay. Thanks very much, Larry. With the four-valve engine, obviously the cam drive is a major issue. Durability, noise, and the size of that package were the key ingredients that we were trying to achieve on this engine. It is a chain-driven job.
In regards to why do we have to have a top speed and so forth, there are many...
I think the answer to that was the one we just heard from McClellan here from the audience, which is we didn't say yet that we will. But there are things like tires and other vehicle considerations with the engine that must be sorted out. We have to know that the entire vehicle is compatible with that speed, and I think that's the answer at this point.
As from the engine viewpoint, Roy, we'd probably say it's a Tiger, rearing to go, and it doesn't care how fast.
Absolutely. Absolutely.
Okay. Very good.
Okay. Thanks very much, Larry. With the four-valve engine, obviously the cam drive is a major issue. Durability, noise, and the size of that package were the key ingredients that we were trying to achieve on this engine. It is a chain-driven job, as you've seen here during the assembly. There is a single silent primary chain, a link chain, that drives an idler. And then from that idler, there are two separate dual roller chains that go up to the individual cylinder heads and drive the four cams. There's a total of 7 guide blades for the chain for keeping it silent and for durability reasons. And 2 of those are hydraulically tensioned on the slack side of the chain, as is being indicated here. There's 1 of those tensioners per cylinder head. They attach right into the cylinder head and operate against the slack side of the chain. What that makes for is a small cam sprocket. And it may seem incidental to it, but remember that 22-degree, very narrow valve angle, and we needed to take the ratio reduction at the idler in order to be able to achieve the 2-to-1 reduction between the crankshaft and the idler so that the sprockets at the top could be a very narrow construction. What that did was then take that widest portion of the cylinder head, as you can look at it there, which is right there at that sprocket housing, and made it the same width as the rest of the cam cover, and that contributed to that mandatory 675 millimeter overall width. The precise valve timing is obviously an issue on these jobs too. You can't have good ignition control and then have the cam control not accurately timed to the crank. So what we do is we pin the camshafts in place in the cylinder head relative to top dead center of the crankshaft. Once you've got the camshaft pinned in place, then the sprocket is free to rotate until it finds its position in the chain link. Then a pin is put in through an index wheel that is then tightened to a flat circle or half circle on the end of the camshaft, and that whole assembly is held in place with a washer and screw assembly, as you've seen there. That brings me to the to the final issue on the design of the engine, and that's the accessory drive. The sides of this engine are clear, except for the exhaust and the catalytic converters and the space for the engine mount. There are no oil filters, there is no starter, because the starter is a gear reduction motor, and it mounts in a clean, dry location in the valley of the engine, and it mounts to a flange at the rear end of the case. And the front end of the engine, driving the rest of the accessories, is a 6-groove single serpentine belt with a spring-loaded tensioner. Now, that's a similar situation to the ones that we have on the Corvette today. However, excellent alignment of those accessories is achieved by rigidly mounting each one of them to a major casting at the front of the engine instead of on traditional brackets. What that package did was tie the 4 accessories all to the front end of the case: power steering pump, the water pump, the generator, and the compressor. It made, again, for probably the most significant thing on the accessory drive, once again, all of them are compactly arranged either in the valley or out front of the engine so that we do not infringe on that 675 millimeter requirement. So what we've ended up with here is what you're seeing in front of you and what I call a high-density performance machine. It's 600 pounds. It's got 50% more power than the engine than the base engine in the car, and it has 30% higher torque, which I think the torque and the displacement are leader in the industry. We're still expecting, in fact, we have vehicles on a regular basis that are running at 22.5 miles per gallon on the emission test, which means that the guzzler law can be met. And most of all, it fits into a 27-inch by 27-inch by 27-inch box, as well as into the Corvette. And that is a monumental achievement for an engine of that power and that displacement. And I think in sort of a mechanical way, it it achieves what was one of those other goals, and that is that it has what I consider a beautiful appearance. That's up for votes, but I really love it. So that brings me back to Fred Schaffsman's original criteria. Again, we've met most of those, but I want to cover the issue here of the fuel economy target against performance. We're going to go on to that, or good? Okay, very good. Now, on the left-hand side, remember that what Fred was showing there was fuel economy. In order to plot all the cars together, you have to put in a factor of weight. You can't have a 2,000-pound car and compare it with a 4,000-pound car. So it's a fuel economy index, including a factor of weight, against the acceleration performance. And that arrow was technology. The number one, what all of those numbers there are on the curve are the Corvette competition. The arrow, as you remember, is the technology line, and it pushes up and to the right. The number one, we're kind of proud to say that even today, in comparison with the other vehicles, there has been an exceptional achievement on fuel economy versus performance in the current Corvette. And that's the number 1 dot there. The number 2 dot, that is another increment up and to the right again, is the LT5 engine. And if you'll notice that that is the fastest car on the sheet. It actually surpasses the Lamborghini Countach, which is the next closest on that acceleration side of the curve. But you'll notice that the Countach, which is number 3, is really kind of off chart here relative to fuel economy. They do not pass Guzzler. I don't think that's their objective. The other engines that I think are superior on the fuel economy here, there is probably the General Motors Quad 4 engine, but it's in a significantly smaller car, and that one is what we are very nearly matching there on the fuel economy index of it, but that car is 3 to 5 seconds slower. So I think that from the standpoint of the original objectives and where we stand on the program today, that we fully expect to meet all those original criteria that were set by Fred and Dave. I think before we have the questions here this time, we're going to cover not only this portion, but I think we can cover the questions on the entire engine at this point. And before we do that, what I would like to do is ask all of the speakers to come on up here and we'll gather around. I think at the beginning, I forgot to mention that, that this is a joint project between the three of us, and in fact, the assemblers are not just from one place. Chris Allen is from Mercury Marine, and Ron is from CPC, so we have a team there. Now, these are the guys who put it together while you were watching, so I'm going to ask them first. I got to be cautious on these things. Ron, what do you think? Think we're ready? Chris, what do you think? Okay, manufacturing's got some involvement in this thing, too. So, Bud, what do you think?
I think we ought to give it a go, Roy.
Gentlemen, start your engine. Okay. Now that part's a little bit of the theatrics, and there's some amplification there too. But at the end there, that little light hum that you heard after that initial roar, that was the pussycat. So I want you to know that we got both ends of that deal. Now, my cohorts all sat back down here again.
Back up here,
Come
gentlemen.
on up here, guys.
And Clara Johnson, where are you, Clara? We have, it's coming up here right now on about a little after about 12 o'clock, so time is beginning to get away from us. We'll take all the questions you have here. What you need to know is that these guys are going to be here all afternoon. The hardware will be here. We have a vast array of stuff behind the screen, so you don't have to panic if it appears it's getting far away from us. Chubba?
How does the 600-pound weight of the LT5 compare with a comparably dressed current Corvette engine, and what's the red line expected to be?
The red line is going to be 7,200, and that is fuel shut-off. It's purely an engine damage issue. We don't know that it, in fact, I'd say we'll have several tests going well over that, but there is no need. The power is at that point not increasing any longer, so we're going to have fuel shut-off up there. What was the first part of that? I'm sorry.
The weight.
Oh, the weight. The weight is it's 6% heavier, even in all aluminum, because of the additional hardware. 6% heavier. Remember, in order to get the structure in the lower case, even though it's aluminum, that's a major additional weight. The aluminum, there is on the current Corvette, as you're probably aware, aluminum heads already, and the dual overhead cams, and the four of them obviously add other weight. So it's an important achievement, and we needed to do that, by the way, as part of the fuel economy achievement. You cannot have a car going up in weight significantly and still achieve fuel economy, even with this kind of technology.
Roy, I might add, with all of that the LT5 has, it's only 39 pounds heavier than the L98, comparably dressed.
Is there a Mercury version of the engine or a Lotus version of the engine, and will there be?
Bud, you've been doing most of the talking with General Motors on there. Why don't you answer that?
Okay, question is there a Mercury version or a Lotus version, or is there intended to be? Yes, there's intended to be a Marine version of this engine, and we hope to have it available, of course, after we get the design and manufacturing finalized for the ZR1 is first priority. Then we plan on developing a Marine version.
Rick Mears needs something to pull that ZR1, or to use behind the ZR1, right, anyway, as it goes down.
That's right, that's right.
Yes.
There were many questions asked about horsepower, but no mention was made of the exceptional capability of this, or potential capability of this engine on torque and on the use of the overhead cams and on the on cam design.
Well, if the question was, we mentioned the exceptional power, and maybe didn't stress the exceptional torque. At 370 foot-pounds, it is the world leader on torque. So if I missed that, I missed an important part.
What is the peak torque on this?
Pardon me?
What is the peak torque?
370 foot-pounds. Again, there's still a range in there. We would expect, and the exhaust, part of the reason that we hedge with it at 10 horsepower or so is that noise laws, pleasability of the final vehicle to the customer does change the back pressure in the system. We have had mufflers on this job, or exhaust systems, that run all the way from 9 inches of back pressure up to to 15 inches of back pressure. And until that final exhaust system for pleasability suits the needs of the car, you can't come out with the exact final advertised power. So that's really the only reason hedge on the power.
Sir.
From the camshaft standpoint, which I think was the second part of that question, there has been considerable development, and there are two camshaft lobes on the inlet camshaft. One of those is intended on the primary to accentuate the fuel economy needs. The secondary one, the one that opens when those port throttles open, those are there for achieving the maximum volumetric.
Roy, if I just add one thing, maybe to show you where we are on torque. Suppose you take a base Corvette L98, and it's got a 6-speed manual transmission, the new one for 1989 we're talking about, and you're at, say, 700 RPM, and I'm at, in the LT5, of course, at 700 RPM, and we'll race in 6th gear, 700 RPM to 1200 RPM. And I think I know who wins. Okay? So the torque is excellent. It's better than the L98, even at those low engine RPMs when you get the whole package and everything else is equal in terms of N/V ratio, car, and that type of thing.
Yeah, yes, if you ran the engine at 7,000 RPM in 6th gear, what speed would the car be going?
Yeah.
We're going to have to take a vote on that. Ian?
It runs top speed in 5th gear. 6th gear is pure overdrive,
All
so
right,
you can't achieve 7,000.
Say 5th gear.
So it's 260 miles an hour or something in 6th gear, so it can't be achieved.
In 5th gear, then, what would that speed
I don't
be?
know what the maximum speed of the vehicle is at the minute.
We can go over, why don't we talk about that. Gordon Corrigan's here too with some of the transmission ratios that we'd need for that, so we can go over that in any detail you wish.
What's the horsepower reduction if you trigger the NOx sensor for using 87 octane unleaded?
Okay, Ian, why don't you comment on that?
There aren't any horsepower reductions with premium or regular fuel. The place where you have detonation limitation is down at low speed of the engine when you're running with a 91 octane fuel, so we don't lose any power at the top end.
Can you, if I understand correctly, the secondary intake valve opens mechanically even when the throttle valve itself is closed. Can you elaborate on what dynamic effect that has in the combustion chamber with that valve opening at the lower horsepower ranges?
I didn't see what the question was.
I think what you're saying is if the throttle valve is closed, what does that do to the combustion efficiency because the valve, the inlet valve, is still operating against that closed valve? Is that correct?
Yes.
Ian might want to comment afterward, but what you're operating against is essentially a dead-headed system there. So for all practical purposes, the combustion chamber does not know that valve is still opening and that there's no air coming in, except from the standpoint that by having the one remaining valve that is open with the throttle open, the air is entering from one side only and tends to improve the swirl, which again assists in the fast burn or the early initiation of fuel burn, which is important to the low speed efficiency and the fuel economy. Ian? Any other comment on it?
No, excellent.
Here one for Mr. Halberson.
First of all, I'd just like to say to be complimented on this engine here. It looks like it's going to be a heck of a product. However, on first impressions from a service standpoint, it appears that it might seem a little bit complicated to the average Chevrolet mechanic. And I was curious as to what type of dealer training programs that you folks have put together when you introduce this engine to the dealership network so that it can be properly serviced.
That's a good question. Larry has been working with the service network now for over 2 years. We wanted them in from the very beginning. In fact, they are going to be participating with us in an ongoing field test program that will precede production on that engine. Specifically, though, we are not taking any chances on this engine at the very beginning of the program with either the service procedures or in not being aware of some detail that might have been overlooked in manufacturing or engineering. We're going to have the blocks, if that is the problem, if the short block or the head assembly and short block assembly are at fault, we're going to pull that whole assembly and send it back to Mercury Marine where the service will be done initially until we know what every possible problem could be in service. Beyond that, Larry, there's a lot of detail on the service part. You might want to comment.
Mercury, and then they ship him another motor to put in?
The point is, would the dealer pull the engine out, ship it to Mercury, and then Mercury repair it and send it back? That's essentially what happens, but there's a key difference, and that is that the block that we are sending back has its brother sitting back at Mercury Marine or at the service location, and that'll be sent immediately to the dealer. So we hope not to increase the service time, but to minimize it and also gain the greatest experience.
I'd like to preface my question by saying that this is an incredible breakthrough for Chevrolet and Mercury Marine and Lotus, and that I'm very pleased to see this engine in the marketplace. I do have one question, however, regarding the reliability of the engine. In the use of aluminum alloy liners with silicon, is there any concern, since there wasn't mention of whether the rings are zero-gapped or otherwise, is there any concern about ring end gaps scoring the cylinder liners?
Okay. Ian, why don't you start on that? I've got some comments on that, too.
Excuse me?
Go ahead.
All our development work and validation work so far, we have no problems with the Nickersill or with the liners. We're still working to ensure that we get the right performance, reliability and durability out of the ring pack, but I can honestly say that we haven't had any ring pack scuffing just throughout the whole life of the development of the engine.
You know, maybe you'd like to innovate on an engine, and I think there isn't any question we've done that. But there are some things you don't want to take any chances with. That's one of them. That liner material, that system, was initially developed by Mahle in Germany, and it was been in production and in racing by Porsche for over 8 years now. We have talked with Porsche themselves on trips over there, and Mahle has been in contact with all of their service. They do not have a service problem, and that is our objective on this engine. And with the aluminum bore, probably not so much the compatibility issue. That's not the whole story. It's obviously this coolant loss. And one gentleman over here asked how we protected against that. One of the reasons for the coolant level sensor that is in the cooling system of today's Corvette is just that. You do not want overheat without at least 2 warnings. And so that is one of the criteria, and we've got that in the vehicle.
We've tried many different ring gaps and configurations, yes.
Have we tried different ring gaps in this engine?
Yes, and the answer to that is yes, we've tried different rings and different ring gaps, just as you would in any normal engine development program, to give us best life and best wear.
Regarding front engine dress, with your new design eliminating bracketry, were there any obstacles or hurdles to overcome with that new type of setup that you have?
Oh, boy. We haven't introduced Gib Hofstetter, and he's been sitting here quietly, but I will tell you, I think there's about a 40 thousandths not interference, but clearances.
Gib, come on out here in the light, so
he's going to need that.
I can honestly...
It'll take a long time to explain all the problems, but it just had to be all juggled. All these components had to be juggled. Essentially, you threw them all up at one time and guided them all back together so they would fit.
Everybody's made a big play about the width of this engine and how it had to go between the rails. There's also been a great deal of hard work on the length of the engine to make sure that it would fit up between the firewall and the front stabilizer bars on the chassis. And without Gib, I think we wouldn't have done it. There's been a tremendous amount of synergism between Chevrolet and Lotus, and making the packaging of the front of the engine has been one of the biggest challenges of the whole engine.
You ought to go backstage here is the components still all laid out, and if we can find a way to do it, we'll show you how the two accessories that fit in that valley fit. There is not a lot of clearance.
And you'll
It
have
has to keep it precise.
ample opportunity today and tomorrow to observe how that thing nestles in there. It is now coming up on 12:21. We've been here for an hour and 40-some minutes. Why don't we're going to raise these curtains back here now. We've got the hardware back here. These gentlemen are going to be around here, Bud and Ian and Larry and Roy and Gib and Fred and David and almost everybody. Stick around. We have delayed lunch, so you don't have to panic about that. Let's see, the cars and trucks going on the little ride parties are now parked in the municipal parking lot. As you walk out this building, they'll be on this lot over here on your left across this little street. That's where you need to go. We're going to try to run that thing on schedule, and if your schedule shows the first flight is leaving at 12:45. So that is going to be a little bit quick for those guys. However, we can handle that. Okay, any questions? Housekeeping of a housekeeping nature? Then why don't we pull the curtains? You're welcome to walk around back here, and you're welcome to go on out there and begin lunch. We will see you all together again tonight when you're all back here, and we'll put you on some buses, and Mr. Hall plans to entertain you. Okay. Rob St. Francis, see me.
Before Corvette ZR1 hits the highways, but we want to keep you up to speed on it. As you may recall, last month we showed you how engineers put together the LT5, that new engine available in a few 1989 Corvettes. The 375 horsepower 32-valve double overhead cam V8, designed by Lotus and developed by CPC Engineering, is actually being built under contract by Mercury Marine in Stillwater, Oklahoma. This is where Mercury produces its MerCruiser stern drive and inboard engines, many of which are based on marine conversions of standard GM automotive engines. Now, some of you have got to be wondering why we asked a boat engine builder to put together our powerful LT5.
There is no one in the world who loves to go faster and for a higher percentage of the time than the boaters. When you get at the wheel of a boat, you know, there's really two throttle positions, maybe three, but two. One is idle, one's wide open throttle, and then if you're going to be out there for a while, you pull it back to around 3/4. So these people in the marine industry are good at high speed, lightweight, and that's the aluminum technology, and medium volume at good quality levels. So when you talk about Mercury Marine, you're talking about people who have been dealing with high performance and lightweight and excellent quality for a lot of years.
Mercury Marine is a world leader in highly engineered aluminum castings, which is important to note when you consider that the LT5 is the first all-aluminum production engine of its kind manufactured in the United States. Though Mercury contracts out much of the foundry work, more than 95% of the highly specialized machining is done in-house. Final assembly is carried out at a series of workstations in an area closed off from the rest of the facility to maintain a clean environment. The engine is as smooth as it is powerful. Just ask the folks at Mercury Marine, who test each LT5 on a dynamometer.
It was Christmas Eve when we started up and fired up the first LT5 engine that was built here in Stillwater. And one of the fellows was telling me with quite a bit of enthusiasm how smooth it was. And he says, I can balance a nickel on it, it's that smooth. And I said, I got a buck says you can't. And so he went over and we were running at about 800 RPM and he put the nickel on and it balanced very, very nicely. And I signaled the guy in the dyno room, you know, run it up a little bit. He ran it up to about 1,000 RPMs and Chris says, you know, that isn't what we agreed on. And I said, well, run it up to about 1,200. We did that and started running it up to about 1,500. And I reached over and picked the nickel off and put it in my pocket. And of course I had to ante up the dollar, but I've demonstrated that several times since then.
at idle on the test stand. It is an extremely smooth engine. On the single injectors, it is a very, very tame engine, and when you step on the accelerator, it is just beyond description.
You'll want to pay close attention to what's happening with corporate average fuel. How's this for a winning team? Corvette ZR1 and Indy 500 champ Rick Mears. The two will be featured in customer brochures and a hardcover book available for ZR1 buyers only. Car and Driver magazine writer and former racer Pat Bedard recorded Mears' impressions of the ZR1 for the promotion. Of course, for the whole story, you'll want to read the book that comes with the purchase of your new ZR1. But for those of you who can't wait, here's a taste of what Mears had to say.
The first thing that came to mind and kept coming to mind all the time I was driving it is that it was fun. It was a fun car to drive. And I think it's very important. You know, it's a true sports car. I think one of the key features that I really like, other than the horsepower that it's got in the engine, is the shock system that it has. You know, being progressive with speed, the valving changing, the dampening, and then having, you know, 3 different settings to choose from and to play with. And it just seems like the faster you go, the more you lean on the car, the better it works, you know, with the progressive shock.
Meanwhile, about
One of the things that we liked so much about this project with Chevrolet on the LT5 program was that it was a marvelous opportunity for 2 companies who are respective leaders in the markets that they serve, 2 great American companies coming together to put just a world-class product into the marketplace that is going to literally get the attention, it already is getting the attention of the world. It was a project that General Motors certainly could have undertaken on their own without us, but there were some common needs, common objectives that were met by Mercury participating, and we're just real happy to have played a role in it.
We're machining the cylinder bores, doing a rough finish and the finish pass on the cylinder bores. We do the head surface, we do the seat where the liner, piston liner sets on, and we do some side holes, the crank sensor hole on that crankshaft just went around. This is where we start to marry the block and the crankcase together. Crankcase is then assembled on here and the main bolts put in. The main bolts are torqued up in 3 stages, 40, 80, and 125 newton meters. Each stage goes to a specific bolt pattern and we torque them. This gives us a readout up here. From the bottom of our tolerance green to green, that is 4 10,000ths of an inch. Cigarette package, the cellophane off that is roughly 5 10,000ths of an inch. So we're holding a very small tolerance on the diameter.
Putting it on a balancer, spinning it at a preset, predetermined speed.
Okay, this is the start of the cylinder head line up here. We'll take it through here to the back into assembly. This cast has Burmel in England. This here is a Mercury Marine design machining cell to do cylinder heads. For all the hose that we got to cut, we had to have something rapid, something fast that'll remove a lot of metal and drill a lot of holes. As you can see, there's a lot of holes to be drilled. Unbelievable how to, yeah, you could get anything. So all the machines virtually have coolant chillers on them. If y'all want to take a look at this for a minute, every time he gauges a part virtually, it gets recorded in this data pewter. So it'll print out various charts, histograms, etc. to tell us how well we're doing. And we also have record history for parts.
This is a Sheffield RS-50 5-axis direct computer-controlled coordinate measuring machine, or CMM for short. Its major application is for the dimensional inspection of our cylinder blocks and cylinder heads. Currently, we use a system whereby our operators on the machine floor submit a part to the CMM at predetermined intervals. The operator then visually inspects the part to ensure it's clean and does the preparation for inspection. The part's then loaded onto the fixture, and the operator loads a pre-written part inspection program from the computer keyboard. At that point, the system takes over, makes the measurement, and presents the inspection data to the printer. The machine is accurate to within 4 microns volumetric accuracy, that's 1.5 thousandths of an inch, and repeatable to about 1.5 microns, or 60 millionths of an inch.
Now there is also a baffle that fits down in there. Looks like this. This just retains all the oil. Right. A windage tray.
Why have you machined this little?
Those are for clearances at the foundry where they make these. Bill will show you what he's doing. It'll compress 8 valve springs at one time. Now what he's doing there is those tools there will center the top hat over the valve stem as they're compressed. Margarita is assembling the secondary port throttle linkage to the head. What she's doing now is she'll be locating, centralizing the butterfly itself.
It's already perfect.
Right. You've got 2 fixed blades, one here and one here.
Now how do you set up all of the timing of all the cams and everything?
Okay, the extra deep slot I showed you down there on the crankshaft. And once she's done, she's got the crank in position, the cams in position, the vernier sprockets here will be lined up, and these pins installed in there. One of the unique features about this engine is that the power steering pump, the air conditioning compressor, and the alternator are all in a fixed position.
The engine is capable of approximately 7,200 RPM. It is good for almost 400 horsepower. Right now, the engine's computer is idling the engine. It's also taking care of all the spark and fueling functions for it. It's measuring what's happening in the exhaust stream and keeping a very, very accurate air-fuel ratio. So it runs very lean for good fuel economy, very good emissions. It's a big criteria of the engine. So we tried it. I think Dwayne's part he likes the best is just letting the engine eat. He likes making horsepower. He likes the way it sounds at $6 grand.
We at Chevrolet are very proud of the Corvette ZR1 and for what it represents for General Motors, and we're particularly happy to have Mercury Marine play such an important role in this project. When I look over the facilities, it reminds me more of a race engine shop than it does a engine assembly operation. Mercury Marine has been a part of this project from the first considerations on how it would be manufactured. Its capabilities in precision manufacturing of aluminum parts and its experience in high-performance engines is known worldwide.
We pride ourselves in being world leaders in precision engineered aluminum castings. We have full die cast facilities here at Stillwater and our major die cast in Fond du Lac, Wisconsin with our own aluminum smelting operation. And our strong expertise lies in flexible manufacturing. Within Mercury Marine, we now have over 200 pieces of computer-controlled numerical work centers and lathes. I want to just touch for a moment this morning on simultaneous engineering and how it helped us establish a process to bring this from basically a design on a piece of paper to production in less than 2 years' time. And I define simultaneous engineering for us at Mercury as just simply engineering and manufacturing working together from the onset to develop product and process to ensure consistent quality of the LT5 engine. It's just that early involvement, working together to talk not just about the design of the engine, but to talk about the process, the quality, how you're going to maintain consistent quality day to day, and we've had an excellent relationship with Chevrolet and Lotus to talk about manufacturing problems sometime when the actual base design was not fully cast in concrete. So it's helped us work that way. We had a bunch of people that had a common objective to bring out a world-class engine in record time.
This is the News on 6, the 6 o'clock edition, with Clayton Vaughn, Karen Carlson, meteorologist Jim Giles, and Bob Stevens with sports.
Production is underway in Stillwater on what is being called the hottest engine in the world. It powers the new Chevy Corvette to an unheard-of speed with motorboat technology. Rick Peterson reports.
You're looking at possibly the fastest production car in the world, the new Chevrolet Corvette ZR1, due out in 1989. Chevrolet won't confirm or deny it, but the car is rumored to go faster than 200 miles per hour. The secret to this new muscle car is a lightweight, highly sophisticated, all-aluminum engine. But the engine is not being built in Detroit. It's being built by Mercury Marine in Stillwater, Oklahoma, an outboard motor company that specializes in aluminum design.
Mercury's capability in high-speed performance engines, their experience in aluminum casting and machining is absolutely perfectly suited to this particular engine.
To produce this high-performance, high-tech engine, Mercury Marine and General Motors joined forces and invested $16 million here in the Stillwater plant. So workers who used to make boat engines are now making car engines. And for fun, they like to bounce a nickel on top of the engine to see how long it'll stay up. This one held through 2,600 RPM, cruising speed. It passes. One employee told me the car is so fast it should be declared illegal. But all are proud to be making the hottest engine in America, right here in Stillwater.
Then when you see it in the magazines, and then you can say, I built that engine. It kind of gives you a good feeling.
Spirits are high. It's getting pretty exciting as far as getting close to production.
When the speed limit is 65 miles per hour, why build a car that can go so fast?
Well, you got to remember that, well, that's an age-old question, I suppose, but acceleration performance, the ability to pass safely.
Whether you believe that or not, a muscle car revival is underway, made possible by a boat company in Stillwater. Rick Peterson, Channel 6 News.
And Rick says the new Corvette should be in the showrooms in March.
Now, from Northeast Oklahoma's news leader, Charles Ealing, Leanne Taylor, meteorologist Don Woods, and John Wall Sports. This is News 8 at 5.
Imagine driving from 0 to 60 miles an hour in just 4 seconds. Promoters say the new 1989 Corvette can do just that. The car's speedy success could drive some big money into an Oklahoma company. News 8's Scott Gordon reports the Corvette engine is being built in Stillwater.
Here it is, General Motors' answer to Ferrari, Porsche, and Maserati. The new Corvette ZR1 has hit the streets early next year. Estimated price tag, $50,000 plus. What makes this machine so unusual and so expensive, its promoters say, is its engine, put together at Stillwater's Mercury Marine assembly plant.
And it's got what we coined a tiger and a pussycat personality. At low speed and driving around town, it's a pussycat. And when you want to turn it into a tiger, it's unbelievable.
Unlike most motors, these are all aluminum and boast 32 valves and 8 cylinders. The work going on here represents a major change for the American automobile industry. Companies like General Motors usually manufacture their own engines. This is believed to be the first time a manufacturer specializing in boat motors has stepped over into the car business. GM executives say they chose Mercury Marine because of its expertise and latest computerized technology.
5-axis, direct computer control. I think we're state-of-the-art on the engine, and I know Mercury is state-of-the-art on the manufacturing. So we think for the industry in the United States and in the world, we're going to throw out a new challenge.
No one is saying exactly how much the GM contract is worth to Oklahoma, but the real payoff could come down the road with future projects.
There's a potential for that, yes. There's a potential for us to do further work with General Motors on specialty engines of this.
When production gets revved up to full speed, this plant will crank out 18 engines a day. Not a lot compared to any modern production line, but still quite efficient for what its makers are calling the world's quickest engine. Scott Gordon, News 8, Stillwater.